Okay, today we want to talk about a simple ODE model for population growth. So let's see what our example says. The size of a bacteria population is initially P naught, and the population has grown to 5 P naught after 3 hours. If the growth rate is proportional to the population at any time t, assuming that the growth rate of the population is proportional to the population, and this is the key thing for us later when we want to write our differential equation, how long does it take for the population to double? Or let's think about this problem together. I think the first thing that we need to do is to give a name to the main variable of interest here, which is the population. So I'm going to start my solution by giving a name to population. I'm going to call my population P of t. I'm going to use the letter P, and P is a function of time here. So here is the solution. Let P of t be equal to bacteria population after t hours. After t hours. As we shall see in a moment, there is a differential equation that this P of t must satisfy. There is a differential equation that governs P of t, the change in P of t. What is given to us in the statement of the problem is that at t equals 0, P of t is equal to P naught. P naught is some given number. And at t equals 3, P of t is equal to 5 P naught. So it is given to us that P of 0 is equal to the known number P naught, and P of 3 is equal to 5 times P naught. All right, very good. So that we know. What is the goal here? What are we asked to find? Our goal is find t, I'm going to call it big T, the doubling time. I'm going to use the letter big D for the doubling time, such that P of big T is equal to 2 times P naught, because it says how long did it take for the population to double, right? Or that is the goal. And in order to do that, we're gonna start by constructing our ODE model. I want to find the differential equation for this P of t, and it's very easy to do that based on the assumption in the statement of the problem where it says the growth rate is proportional to the population. Remember, the derivative with respect to time is the mathematical translation of the term rate of change, growth rate. So here what the statement of the problem says is that the observation shows that the rate of change, the derivative with respect to time, is proportional to the current value of the population. So this statement that we have in the statement of the problem immediately tells us the differential equation that governs this P of t. So let me write this down. The assumption that the growth rate is proportional to the current value of the population, to size of the population at any time, to the current size of the population at any time, immediately tells us what the governing differential equation is, based on, again, that key interpretation of derivative with respect to time. Derivative with respect to time is exactly the rate of change. Leads directly to the conclusion that P of t satisfies the differential equation dp dt equals some constant, our constant of proportionality, which I'm going to call k, times p. And p here is a function of t. dp dt is equal to k times p of t. This is our differential equation, the differential equation that must be satisfied by p, because we know that the rate of change is proportional to the current value. Rate of change, current value, and that is the assumption based on observation. People saw that for this particular species, bacteria, the rate of change is proportional to the current value. So I'm going to call this a star. This is our main differential equation. This k is the name I use for the constant of proportionality. At this point, we don't know what it is, but hopefully based on the information given to us in the statement of the problem, we will be able to figure out what this k should be, where k is the constant of proportionality, which by assumption we know it exists, right? Constant of proportionality. Awesome. Now, how do we solve this differential equation? Folks, you can obviously solve this as a separable first order ODE, but this particular equation, where the rate of change is proportional to the current value, this one is so fundamental, I advise you to actually memorize the solution to. So this can be solved as a separable equation or even as a linear equation, linear first order equation or separable first order equation. But this particular the differential equation where the rate of change is proportional to the current value, it's good to memorize the solution to. Let me remind you of this general fact. Here we go. So if you know that the derivative of a function u with respect to t is proportional to the current value of u, this k is a constant number, then you can immediately say u of t is equal to c times e to the kt. This is the general solution to the differential equation. C is an arbitrary constant. K is the constant of proportionality that you see here. So the solution is exponential. You can use the method of separation of variables, for example, to arrive at this result. This is the separable equation. I'm sorry, you can use the method that we had for solving the separable equations to arrive at this result. But memorize for this particular simple equation, it's good to memorize the solution. All right, so I immediately know that because of this reminder, I immediately know that the general solution to my equation is P of t equals C e to the kt. At this stage, C is an arbitrary constant. Very soon, I will determine what C should be based on the available information. I will determine what K should be based on the information that is given to us in the statement of the problem. Now, before focusing on the problem at hand, let me make a few observations, a number of observations about this ODE model and its solution, and then I will focus on the problem at hand. I will do the job, okay? So, let me make a few comments about this equation. Let me actually write this. Let's make a few observations, a few observations about this ODE model for population, ODE model for population dynamics. This is dp dt equals kp and its solution, which is P of t equals C e to the kt. Or so And introducing some terminology. If k is greater than zero, if this constant of proportionality is greater than zero, people usually refer to it as the growth constant. In this case, we are dealing with population growth. As time passes by, the population will grow exponentially. We call it a growth constant. If this constant of proportionality is less than zero, we call it a decay constant. This time we are dealing with population decay, a decay constant. Okay, so far so good. Let me also make this comment very quickly, that please notice that at time t equals zero, P of zero is equal to C times e to the power of zero. So this C that you see here, as a matter of fact, is your population at time t equals zero, right? The initial population. Keep that in mind. I will come back to this very soon. Now, let's focus on the case that we have actually population growth, the case where k is greater than zero. When k is greater than zero, the equation dp dt equals kp tells us that the larger the population, the larger piece the current population is, the faster it grows. The faster it grows, because the rate of change is equal to k times the current population. Now, this idea that the population is growing exponentially, and the larger the population is, the faster the growth is, it's good. It's useful for modeling smaller populations when we are not limited by the environment, by the resources available, like space, energy, food. When there is unlimited resources, yes, the population will grow, maybe exponentially, based on this model. However, in reality, normally there will be restrictions by the environment. It's not the case that population can grow indefinitely exponentially. There is like a maximum population that can be sustained by the environment. So this model is good when you are dealing with smaller populations that are not limited by the environment, by the resources available to them, such as food, energy, space, and so on and so forth. But generally, we have to come up with a better model if we want to consider the very real thing that normally the resources are limited and there will be a maximum population that we can have. And I will talk about that in another video, like a maybe more accurate model of population the dynamics, which we will call the logistic model. So this is the exponential growth model, and later in a different video, I will talk about the logistic model, which considers the fact that there should be a maximum population that can be sustained by the surrounding environment. So let me actually write a little bit of what I just said. So this can be useful. This can be useful for modeling smaller populations that aren't yet limited by their environment or their resources, like food, energy, water, or the resources available to them, around them. when you have a small population where the growth is unlimited in a sense. But generally, you shouldn't expect this. But generally populations don't tend to grow exponentially forever. Exponentially forever. Without bound. Without bound. Because for one thing, resources are limited. Because for one reason, for one thing, resources are limited. Okay, later in a different video, I will talk about the maybe a more accurate model, which is called the logistic model. Let me actually write that as well in another video. I will introduce the logistic equation. It's another differential equation model as an improvement to the exponential growth model, the model that we are currently considering, to the exponential growth model, this model that we are considering in this video, which accounts for this logistic equation, logistic model, accounts for the fact that there is a maximum population. There is a maximum population that can be sustained by the surrounding environment. Awesome. So, but that is for a different video. Now that we made these general observations, let's go back to the problem at hand, focus on the problem at hand and solve the problem. Going back to the problem at hand, what are the things that we know? We know that P of t is equal to, in this model, in the exponential growth model, C e to the kt. And P at 0 is equal to P0, and P at 3 is equal to 5P0. I'm going to use the available information to find my C and my K. I have two pieces of information, and I'm going to use them to find C and K. Let's start with the fact that P of 0 is equal to P naught. P of 0 is equal to P naught. That means that C times e to the k0 is equal to P naught. That means that e to the k0 is e to the 0, which is 1. That means that C is equal to P naught. P of t is equal to P naught, the initial population, times e to the kt. That is what our model is telling us. The model is telling us that P after t hours is equal to P naught e to the kt. Now let's figure out what K is using the second piece of information. We have P of 3 is equal to 5 P naught. Therefore, P naught e to the power of 3K is equal to 5 P naught. That means that e to the 3K is equal to 5. And how do I find K? We apply the natural log to both sides. And so ln, natural log of e to the 3k, is equal to ln of 5. Therefore, 3k is equal to natural log of 5. Therefore, k is equal to ln 5 over 3. That is our growth rate here. It's a positive number. Thus, p of t is equal to p naught e to the power of ln 5 over 3 times t. Now we have our function population as a function of t. And what was the goal? The goal was to, remember, we want to find the doubling time, to find big T such that P of big T is equal to 2 times P naught. We have. So let's use our formula to find this big T. P of big T is equal to 2 times P naught. What is P of big T? P0 e to the power of ln 5 over 3 e to the power of ln 5 over 3 times big T. I want this to be equal to 2p naught. So what does that mean? I can divide both sides by p naught. That tells me that e to the power of ln of 5 over 3 times t is equal to 2. And again, I'm going to apply natural log to both sides because the unknown is in the exponent. So if I apply the natural log to the left-hand side, that will give me ln 5 over 3t. And if I apply natural log to the right-hand side, I will get ln 2. So that means that t, the doubling time, is equal to 3 ln 2 divided by ln 5. No, you may use a calculator at this point to compute, to approximate this value. It is approximately equal to 1.29. So the bacteria doubled in size of its original population in about 1.29 hours, which is about 77 minutes. So the bacteria doubled the size of its original population, initial population, in about 1.29 hours. Each hour is 60 minutes. 1.29 hours is approximately 77 minutes. All right, awesome. So in a different video, I will talk about the logistic model for population dynamics, which in a sense improves this simpler model, the exponential growth model, exponential decay model based on the K, whether K is positive or negative.